6 participants are there. So anyway, the name of the webinar today is Basics of Wastewater Collection System. It's 2 hours. We'll start now and we'll finish around 12. So that's what there should be, the webinar. And by name, we'll do some kind of like say what we need to do for wastewater collection system. Like so, we'll see a little bit of design plus a little bit of explanation and some definition and terminology and other things like that. So, okay, so the outline that I put it together for this webinar is a little bit of introduction and definition of terms, different terms that we use in related to this kind of topic. Then like types of collection systems, and then types of sewers and shapes of sewers, collection system appurtenances. I mean, different small part of it that we use as additional part of the system management. So basic considerations for sewer design, what kind of assumptions or consideration we have to design it. Then design of sanitary sewers, we'll see a little bit of design of that. Then preparation of contract drawings and specifications, we'll see a little bit of like how they prepare or something like that. Construction of sewers, we'll see some pictures of those when they're constructing, a little bit of process in there. Then the maintenance of the sewer, once we construct it, design it, construct it, and start using it, then we have to manage it. Without maintenance, it will not be in good shape. And finally, I'll show you some example of specifications that we use for different materials, different works, part of works, and other things like that. So I have here, like say, a link here. This is a manual, like I think it's mainly sewer management or other things like that from an engineering company. So I put it in there. You guys can take a look on that. This is a good one. They have a lot of information there. So, okay, the learning outcomes for this topic would be define common terminology used in the wastewater collection system, and explain different types of wastewater collection system, and discuss the basic considerations of wastewater collection system design. Then define common terminology used. Sorry, it should be the same one, looks like. Design a simple circular sewer system. We'll do some example problem here. Then describe the construct specifications of high density polyethylene pipes and appurtenances. So we'll just discuss those a little bit. Okay. So introduction, the water supply of a community is considered to generate wastewater, almost the same amount of water used as supply water. This may not be true, almost the same amount. I didn't say exactly the same amount, but almost the same. Because the main idea is whenever we have used some water in our home, certain part of the water goes to waste. It doesn't make the way to the sewer line. Some of them could be, if we have some water flushed in the like floor in other places, then they will be evaporating. Excuse me, something like that. And some part of it, whatever we use for the lawn watering, garden watering, then they don't go to the wastewater treatment plant, means sewer line. So that's why it's almost like 90%, but I'm saying almost the same because of other part may be coming from the infiltration and inflow from the rainfall and other things, depending on the type of pipes and connection that we use. So that's why it's kind of almost the same. The individual pipes used to collect and transport wastewater are called the sewers, and the network of sewers used to collect wastewater from the community is known as collection system. So this is the kind of definition of what is the collection system means. Okay. So the domestic sewage, definition of domestic sewage would be the liquid waste generated from residences, business buildings, and institutions is known as domestic or sanitary sewage. Industrial sewage, the liquid waste generated from industrial activities or industrial establishment is known as industrial sewage. Just if we say just the sewage, combination of domestic and industrial. If we just say sewage, meaning I'm meaning both. But if I have a separate system, then I have to say domestic, I have to say industrial. So that's what it is. Okay, salage. Salage, the water from kitchen, bath, sinks, and similar appliances from buildings which does not contain human or animal excreta is called the salage. The sewage is like everything that has a whatever in this definition, plus the human excreta, including everything. But the solid is that almost everything except the exclude the like say human excreta. So sewer, a pipe carrying sewage is called the sewer. Sewerage, the system of pipes, is like system of pipes laid for carrying sewage is called sewerage. So three types of sewer system. The one is sanitary or municipal sewer. The other one is the stormwater sewer and the combined sewer line. Sanitary sewer identified as separate sewers, and it is developed to mainly remove domestic sewage from the residential areas. Okay, so by name it's kind of clear that the sanitary sewer is like, so there is domestic sewage that is carried the domestic sewage from industrial areas, other things like that. Then the storm sewer, it is solely used to collect storm water, usually larger than sanitary sewer. Combined is both. It is used to collect both domestic and sewage and storm water combinedly. So basically nowadays, combined sewer system design is not happening that much because of most of the time it is too big to design because of the storm water, especially like say if we have a highly rainfall area, then we have to have a lot of rainfall coming to the wastewater treatment plant, meaning we have to have a lot of treatment facilities, right? A lot of capacity treatment facilities. So sometimes it is kind of impossible to do that. And the combined sewer, another problem is we have to do CS, so combined sewer overflow. We may have to allow it because we don't want to design a wastewater treatment plant that will do the peak of the stormwater as well as the domestic sewage. The main reason is so heavy rainfall happens only a few days a year. So if we design something for that, that means most of the year it would be unutilized, meaning it's a waste of money in terms of waste of design, over design, and other things like that. So that's why we don't do the over design. We design a certain level. So if it goes beyond that, we cannot take care of it. We just leave it directly overflow, allow the overflow. So overflow allows this because of, at that time, since we have a high rainfall, we'll have a lot of water in there, right? So if you have a lot of water, the dilution would be there. So meaning dilution is the solution, right? So that should be another good option for that. Okay, types of sewers is number one, the sewers vary size, collection system, and the location of the wastewater treatment plants. The principal types of sewers are building sewers. That means sometimes called the building connections that are used to convey wastewater, basically wastewater from buildings and like or to lateral or branch sewers or any other sewers except another building sewers, something like that. So this is called the building. I have some pictures that I'll show you. It will clarify more other than just learning this definition. Lateral branch sewers, first element of the wastewater collection system that are used to convey wastewater from one or more building sewers to the main sewers. So main sewers are used to convey the wastewater from one or more lateral sewers to trunk sewers or to intercepting sewers. We'll design or show some of those definitely, like this is the one. All of those, I'll show you some more pictures. Let me see whether I can do some kind of markup here. So I'm going to house. Let's see. Okay, I think this is better. So I can show you some of those. Okay, so this picture will show you a little bit something like that. So I need to erase that. Sorry, I need to erase this part because this is not working. Okay, so this picture will show us different kind of like sewer system. This is the main sewer, and this is a manhole, right? This is manhole, and this is also intercepting flow to the intercepting source, means coming from here going somewhere else. These are the Y connection here. It's coming this way, swap from the houses and other things. There is a connection point. So we'll see some areas like so why we need the like manholes and other things like that. So In this case, looks like this manhole is carrying, connecting like four of them, right? This one, this one, this one, and connecting to the other manhole. And looks like this one is coming here, this one coming here. This is the one taking out, right? This is the one taking out. So all of them are collecting, and this is the only one is passing the wastewater to other areas. Okay, the shapes could be rectangular, RCC, or maybe precast or cast seated. Then the circular, commonly used, maybe concrete or HDPE. The semi-elliptical, RCC, and very stable, horseshoe. So I'll describe all of them a little bit here and there. Suitable for heavy discharge. Heavy discharge means if you have a very high Q, then the horseshoe will be the best one because it's a kind of best good section and other things like that. So that, but as I said, most of the time this is the case. The circular one are used. Rectangular one I have not seen that much because it's not that good. But the rectangular one definitely is more stable because of the orientation and other things like that. But I don't see that much of using it. Mainly circular. Okay, egg-shaped one looks like gives good hydraulic properties even better than the circular. So this is the egg-shaped one. Why it is better hydraulics? Because of, like say, it has a smaller circle in the bottom, higher circle in the top. So if I have a low flow, that means it is good in the circular flow here. So that's could be one of the reasons that it's a good hydraulics. This is the rectangular one, and this is the circular one. So okay, this is semi-elliptical, and this is the horseshoe. This is the horseshoe, it's other way around. This horseshoe, the other one we had here, egg shaped, and horseshoe is a little bit different, right? A little bit different. It's not the same line. Okay, so egg shaped, here is the construction. They're showing a little bit egg shaped one. The small circle always will be kind of downward. I think I may have seen some of it, they use the upward, but I think most advantageous is this one. This is the best way to do that. So that's the egg-shaped one. We're doing something over here. Looks like. So more of those. Here is the manhole that has option to connect the egg-shaped sewer lines and other things like that. So, okay. Collection system appurtenance. Like, so what are the different things we need to use for that? Number one is the manhole. Number two is the drop inlets to manholes, building connections, and junction chambers. So manhole, we know that the manhole is just connecting a few of those. Drop inlets of manholes means if I have to drop some very high energy thing, then definitely this is one of the options. Looks like then the building connections, we have seen that the building connections, we have to do that because we cannot connect all the building by like individually. So we have to have a junction there, then connect over there. Then the junction chambers. So if most of the cases we have more than 4 or 5 connections coming, then the manhole man will be able to take it. Then we use the junction chambers. So when the manhole is not possible to use to do that, then we use the junction chambers. It's a kind of big, like a big box and other things. Pre-installed, could be pre-installed or installed, something like that. So here, this is the kind of manhole section showing here, section CC. If I cut it here and look at this, it looks like that. And this is the vertical section. So meaning in this case, if I cut it here and look this way, cut it here and look the other way, then that's what it will look like. Looks like a big one. So that could be when, I think I have seen something, could be up to 10 to 15 feet with them. So depending on where we are putting the lines and other things. Okay. So manholes are provided at every change in alignment. So when it's going from high elevation to low elevation or low elevation to high elevation, low elevation to high elevation, definitely we need a pump over there. But most likely it is a high elevation to low elevation, then that's what we use. Every change in gradient, right? Alignment gradient, meaning in this case, every junction of 2 or more sewer lines, yeah, depending on, like this one could be for 2 or 3. Most of the time, maximum is 4. They cannot take more than 4 lines, depending on the size of the manhole. If it is more than 4, then it doesn't work. Then we have to go to the junction chambers. So heads of all sewer and branches, the starting point. then every change in the size of the source, yes, because when it's changing the sizes, then definitely this has to be the action. So, okay, so I have a regular interval of the sweat system. So it depends the diameter of the swell line. So based on the diameter, we know like what should be the frequency, how what would be the distance of the manholes for the purpose of maintenance and other things, cleaning and everything like that. So up to 6 inch looks like 150 feet. 6 inch to 20 inch looks like 250 feet. 20 to 36 inch is 300 feet. And if it is greater than 36 inch, means feet there, then it's provided by the authority. At the certain county, city, or the authority, whatever we are dealing with, even the state, they have some kind of minimum requirement that we have to follow. Okay? So if anybody works in a city or anything like that, okay, looks like there is a comment here. You cannot hear me. Can you try to move to my closer? You probably do for okay, sorry about that. How about now? Is it better? Okay, good, good. Thank you. So the whatever I was saying, the authority means like say county, city, or what kind of rules or regulations we have followed. So that's the meaning of the authority. So certain cases, I have not seen more than 300 to 350 feet because of the maintenance issue. If you put too much away, like say high-spaced one, then the issue would be like if somebody needs to go and clean it up, they have to go further away from the manhole. So that's another issue. So 300 feet, probably 350 is the max. But again, as I said, the authority, as provided by the authority, meaning county, city, or the state, they have their own guidelines to follow. Then we have to follow. Okay? So yeah, let me know if you cannot hear me better or anything like that. So. Okay, let's move forward. Any questions so far? You have any questions? So you can raise your hand. Let me see whether I can see your hand or anything. Or I don't know what is the best way to make you speak. Any way to make you speak, maybe. So, yeah, they can. Yeah, I see some of them. They can type in the chat. Okay, good. So we'll take this one as a good option. Okay, here is the collection system appurtenances mode, a drop inlets to manholes. So why we need to do this arrangement? Because this is the okay, this is the manhole looks like, and this is the drop inlet. Why we need to do this kind of arrangement? Because of say this is the high elevation, is the low elevation. So the drop inlet will help to reduce the energy or hydraulic jump or other things like that. So because it does a lot of energy, so we have to make some kind of arrangement over here so that it reduces the energy, damping the energy, and it doesn't break the pipes or anything like that. Okay? So here are some of the information there. Pipe size in millimeter, and the inlets were D1, D2. So these are the combination. Looks like here, this is the D1, this is the D2, looks like, and this is the D. This is the D2. So they have a different guidance here for the design purpose and other things like that. Only we need to design a drop inlets and other things like that. Okay. So here are the connections, building connections, looks like. This is the building structure, looks the building foundation, and this is going deep out, like say, below the building, looks like, below the foundations. I'm not sure how good it is. Like say, if it is the mat foundation, that's a different case. Other than this, probably we can take it to the side. But if it is the other cases like steel structure, then probably it will be like that. So it could be easier. Only mat foundation has the issue. So, so Okay, so these are like say connection. These are like say what is called flexible coupling, meaning in this case it could be plastic or HDPE. I have seen some of those HDPE that have used in their coupling. These are the mainly changing from high diameter to small diameter. Two different diameters adding together is basically require this kind of stuff. So this shows a little bit of trading this way means like probably flowing this way because of the gradient, other things. Okay. Typical junction chambers, like they are larger forms of manholes, as I mentioned that. The one tubular pre-made manhole cannot be used because of the number of connections and other things, then they'll use the junction chambers. As the diameter of the intercepting sewers continues to increase as wastewater from more of these service areas is collected, the precast manholes may not be big enough to be used. So that's why the junction is there. Special junction chambers are constructed on site to connect the intercepting sewers. So that's the main purpose of junction chambers. So then the basic considerations of sewer design. In order to design, what kind of basic thing we have to consider? Okay. So number one is the estimation of wastewater design flow. Estimation of wastewater design flow rates, meaning how much water is coming or wastewater is coming that we have to deal with. Selection of design parameters is the second one. But the selection of the design parameters, we have to see hydraulic design equation. What kind of equation we can use? I will mention some of the equation. One of them, like so we have few of those. I think the Hazen-Williams probably will not do the Hazen-Williams, maybe the other one. So sewer pipe materials, minimum sizes, maximum minimum flow velocities. These would be the consideration of these basic under the basic considerations. Selection of appropriate sewer appurtenances like manhole or junction chambers and other things like that. Evaluation of alternative alignments, meaning we have to see whether if I take the line this way or that way, if I put the curve or if I put the 90-degree band, whether this would be easier or not, what would be the cheaper or expensive, something like that. Evaluation of the use of curved sewers if necessary. Carving is sometimes not easy, but sometimes we need to, probably will do that. So estimation of design flow rates, how we can estimate that. The flow rate of a sewage may consist of infiltration, dry weather flow, which is domestic and industrial wastewater, stormwater for the combined sewer only. Infiltration and inflow could be coming also depending on what they are. We have to consider all of this. So here is the definition of infiltration: is the water that enters through pores, points, cracks, manholes, covers, etc. During dry weather, there will be no infiltration, and hence only the domestic sewage and industrial waste will be conveyed. So infiltration is basically, we have to consider it during the design because of the design will be there for both the seasons, is the dry season and the wet season during the rainfall. So we have to consider that. So during the rains, infiltration will be due to the rise of the groundwater table and from the roofs. The infiltration depends on height of the groundwater level, groundwater table, types of soil in which swales are laid. If it is the sandy soil, then definitely more infiltration would be there. And workmanship of laying the pipes. Workmanship means like say, how the connections are, what kind of connection, whether they are good connection or they have a lot of leaks and other things like that. So then it will be more. Okay. So these are the considerations we have to see for infiltration. Then sanitary sewers are designed for the following flows: peak flows from industrial, commercial, institutional, and industrial sources for the entire service area. So here's the new word we get: service area. Service area, the area what is served by the system that will be designed. That's what it means. Peak infiltration allowance for the entire service area. Peak infiltration for the purpose of taking care of the worst case scenario. So we have to have this. Okay. So sanitary sewers are designed for the following flows. Like say in this case, a peak factor may be selected according to the following table. So if I'm serving like, or this thing is serving 20,000 people, then 3.5, a little bit more. 20 to 50,000 is 2.5. 50,000 to 750,000, 2.25. If it is greater than 750,000, then 2.0. So these are the peak factors. So peak factor mainly we use to design those so we can take care of the worst case scenario if it happens. Okay. So in order to estimate, we have to use some kind of like equations or methods. The first one is called the rational method. Rational method is the best one to use this way. This formula estimates the peak rate of runoff at any location in a drainage area. The formula is expressed as Q equal to CIA. So Q is the flow rate in cubic feet per second or cubic meter per second or liter per minute, liter per second, whatever we use. Then the C is the dimensionless runoff coefficient, depend on the land use. I'll show you a table. I have a table in there with the C values for different options. And the I is the design rainfall intensity, inch per hour. So for a duration equal to the time of concentration, TC of a watershed. So we'll define a little bit of what is the time of concentration, and A is the drainage area in acres. So time of concentration is basically the time that required for a runoff to travel from a hydrologically distant point into the watershed to the outlet. I don't have any picture, but it looks like if you consider a area, small area, and if I know the highest point of that area, and I know the outlet of that area. So this would be like the highest distance, highest point to whatever the time it takes to the water drop coming to the outlet. So this would be the time of concentration. So I will be taken as a inch per hour. So when we take the time of concentration, we'll collect the rainfall amount at the time of concentration. Then if I know time of concentration is 20 minutes, then we can convert it to inch per hour. If I collect the 20 minutes of water, if it comes certain amount, then I can convert it to per hour. So that's what the I value has to be. Okay. So the assumptions for the method, because rational method needs some kind of assumptions, and the steady rainfall intensity. Steady rainfall intensity means continuously raining the same. Right? Is 1 inch per hour or 3 inch per hour is continuously the same. The maximum discharge will occur at the watershed outlet at the time when the entire area above the outlet is contributing runoff. Means the runoff is coming from all the points of the watershed, okay, or the catchment basin, whatever we call it. So then whatever the amount is coming here is called the steady state. Okay. The time of concentration is equal to the minimum duration of the peak rainfall. So if my time of concentration is 20 minutes, then the minimum duration of the peak rainfall, that means I'm assuming, or we have to assume that 20 minutes rainfall was the high intensity. That's the peak rainfall was for that time period. So that's the main idea of the assumption. These are the two assumptions that we have to know that before we use the rational equation to calculate the Q1. Okay. So, okay. The frequency or return period of the computed peak discharge is the same as the frequency or return period of rainfall intensity, design style, for the given time of concentration. The fraction of rainfall that becomes runoff is independent of rainfall intensity or volume. We know that we become infiltration, right? Infiltration, then remaining part becomes the runoff. So the fraction of rainfall that becomes a runoff is independent of rainfall intensity or volume. So that's another assumption. The peak rate of runoff is sufficient information for the design of stormwater retention and retention facilities. So most of the subdivision nowadays, they have to design those as stormwater retention or retention pond because it's kind of required. Basically, for 1 acre, you provide 34 cubic yards for 1 acre areas or something, things like that. There are some guidelines in the stormwater management manual for different states, city, or county. Okay. So limitations of the rational method. Because of the assumptions discussed previously, the rational method should only be used when the following criteria are met. The given watershed has a time of concentration TC less than 20 minutes. 20 minutes I use as an example to say before, but here it is 20 minutes we can use this method, rational method, to calculate Q if the time of concentration TC is less than 20 minutes and the drainage area is less than 20. So these are the two limitations. If it is like say TC is more than 20 and the drainage area is more than 20 acres, then definitely you have to use some other formula, not this one. Okay? So here is the table that shows the C value. You remember Q equal to CIA, right? C was the coefficient, runoff coefficient. So in this case, it depends on the like say use of the the land use plan and other things like that. And so like for the business, commercial, and industrial is 0.09. Why it is like that? Because of like say only 9%, right? 9% would be like say runoff, and remaining would be circulation because it's very small area is paved. That's the meaning. Apartments 0.75. Why apartment is 0.75? Because of apartment most likely it is paid, right? So that's why it would be higher runoff value in this case. Schools are 60% or 0.6 looks like 60% of the rainfall would be runoff. Residential lots 10,000 square feet, 12,000, 17,000 and half acres. Looks like 10,000 is 0.5, 12,000 is 0.45, 17,000 0.45, half acres is 0.2. So if it is half acre, most likely there'll be a lot of areas open or unpaved. So meaning 60% maybe will be infiltration calculation or infiltrate in the groundwater. If it is the parks, cemeteries, and unimproved areas, then 34% would be on the runoff, and the remaining, like say 66% would be kind of like infiltration. Paved or roof areas, 90% would be runoff. Cultivated areas, 60%. Pasture is 45%. 0.45 forest is 3. 0.3 steep grass slope, 0.7. Steep slope 70% because of the water it goes down before it can infiltrate. So that's another reason. Shoulder and ditch areas 50%. Lawns are 20%. Lawns are very good for infiltration. That's why only 20% could be the runoff. Because we use the soil every year, or we do the like say what is called the erosion and other things like that. The soil is loose, so most of the water goes to the groundwater. Most of the rainfall. Okay, so okay, let's try to solve an example problem here. Okay, so this is the example. Estimate the maximum runoff from a drainage area of 20,000 square feet, of which 25% is residential lot, size of 1,200 square feet, 30% is forest, 10% is lawns, and 35% is industrial and commercial for design for intensity of 4.5 inch per hour, for a duration equal to the time of concentration of the drainage stream. So it's given like say total area is 20,000 square feet. So out of this, 25% is residential, lot size is 1,200 square feet, 30% is forest, 10% is lawns, and 35% is industrial and commercial use. And the I value is given 4.5, right? I value is given. So I solved the problem using the Excel. So what I did here, area is at 20,000 square feet, I is equal to 4.5 inch. I converted into feet per second. So what I did, I like say 4.5 inch per hour. So I converted the inch into feet in the per hour. Then I did the per second, 3,600, right? Residential is 25%. So 25% of 20,000 is 500 square feet. C value for residential with 1,200 square feet. C value would be looks like here 0.45. Let's go back to the table and see what the value is there. So 1,200 is 0.45, right? This is the 1.45. So that's good one, right? So then the next one would be looks like forest is 30%. And we mentioned before 30% of 20,000 is 6,000. And the C value for the forest is 0.3. And so on. 10% is the lawn, 2,000. and the 0.2 for the runoff. Industrial commercial is 35%, of 20,000 is 7,000, and this one is only 9%, or 0.09 is the coefficient, runoff coefficient, right? Is runoff. So if I do the calculation here, AC, that means I did multiply this and this with this and this and this, total is this. Now Q equal to CIE. So this is already I have a CA here. If I multiply it with I, then I get this, 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 this. And if I add them up together, I come up with 0.529. So meaning the maximum runoff Q equal to summation of all of those, meaning adding up all of them become 0.529 cubic feet per second. So in order to do cubic feet per second, I have to do the I converting to feet per second. Okay? So that's the amount. So now I know my Q value. So for the purpose of designing, I should be able to design it, right? If I'm designing a pipe system to carry that much of Q, how can I design it? Is Q, the continuity equation is Q equal to what? Area times the velocity, right? Q equal to area times the velocity. So if I know the velocity, I should be able to find the area. If I know the area, then definitely I should be able to find the diameter, depending on what kind of pipe here is, either circular, rectangular, or square pipe. So any questions? Can you give a few minutes to read the question? Okay. So, okay, go ahead, guys, read it, and I'll try to explain it again. Yeah, I think we have enough time. We can go slow. It's not a big deal. So. Okay. Okay, good. Now take a look on that and see whether it makes sense. If you guys have a calculator with you, you can even check some of the numbers, maybe. It will be helpful. So 20% of 2,000 is, excuse me, 5,000. Okay, there's a question in here, why the C value is very low for commercial and industrial. So let's go back to this. For the commercial and industrial is too low because of commercial and industrial, most of the time they have a lot of areas open, meaning they are not paved. Okay, so that's why it is the case, especially in industrial, right? Commercial industrial, like say, if I have a warehouse, a certain case in warehouse, then they have a lot of open areas. Why it is open areas? Because of they don't have a customer coming every day, and they don't need to have a, like say, one parking lot for each 700 square feet. Whereas a shopping center or some other areas, malls and other things, they have to have a more of like what's called the more parking lot, more parking space. Okay, so if it is parking lot is more, meaning more areas are paved, meaning looks like the infiltration would be less. Okay, that means more would be like Serrano. But business, commercial, and industrial, the explanation that I'm giving you, other than the mall and other areas, the C value would be very low because of most of the area would be open, not unpaved. So that's the main reason. This C value based on individual lots are put out for each type. It is, I think, is a lot size that we mentioned, 10,000, 12,000, 17,000 and half acres. So these are, looks like these are based on the study. These are based on kind of study that we did and found that, so these are the reasonable values to assume. So it's not really is a theoretical basis or anything like that. This came out from different studies. So in this case, if you have a 10,000 square feet, 10 lots, say for example, you can use 0.5 for all 10. So you don't need to use individually. You can add them up together and use 0.5 for that. So the question was, is individual lots or total for the each type. This could be total for each type. So it doesn't need to be individual lots. If I didn't understand the other question, please click start course slides, link on the next screen. So I don't know what is the meaning. Is it to me or to somebody else? Okay. Is it that okay? Is explained properly? See values for these methods. So any question on them? Any question on the problem solving? Okay, we can move forward then. Okay, the next, the selection of design parameters, design equation. So design equation, this is the best one that we'll be using. We calculate something Q value from the storm water and other things like that. Currently, Manning's equation is the widely used one to design sewer system. The Manning's equation is V is the velocity of the flow, K over N, and R H to the power 2/3 S to the power half. So I'll explain the terms. V is the velocity of the flow, is feet per second in FPS system and meter per second in SI system international. K is equal to 1 for SI system international and 1.486 for FPS system. Okay, RH is the hydraulic radius. By definition, hydraulic radius is equal to flow area divided by weighted perimeter. So in fluid mechanics, we learned those in there, right? The S is the channel slope or slope of energy gradient line. Is feet per feet, meter per meter. That means if I have a 1 feet drop after each 100 feet, that means this would be 1 over 100, right? This would be 1 over 100. N is equal to Manning's roughness coefficient. It depends on channel materials, surface irregularities, variation in shape and size of the cross section, vegetation, flow conditions, channel obstruction, and degree of meandering. So these are few things depends on. Like I have a table, Manning's table from the Chow book. Like Wendy Chow is a very famous hydraulic guy, right? Open channel guy. So we'll discuss those more in there. I think I have a table here, but anyway. The Manning's equation can be written for the Q also. Q equal to area times velocity. So the final equation becomes K over N, A R to the power 2/3, S to the power half. We already know RH is the hydraulic radius, S is the slope, A is the cross-sectional area, K is a 1 for SI and 1.486 for FPS, N is the roughness coefficient, Manning's roughness coefficient, right? So N can be obtained from tables or the following equations. So here are the equations, N equal to 0.038D 1/6 proposed by this, and where D equal to 90 percentile size of bed material. If you know the bed material and 90 percent crossing is called a D, right? D30, D60, you guys may be familiar with that. So if I draw a grain size distribution curve, percent final with the sizes, then if I take a D90 from there, whatever the size is there, it would be 90, right? D90. And the other one is proposed by Strickler. It's very similar. The other one is 0.038, and this one is 0.017. Right. Other one D to the power 1/6 anyway. Both of them are the same. So this is, if we want to use the equation, then I can use the equation to find the value of N. But here is a table that I mentioned that. So Wendy Chow likes to put this table together. There are 3 options here: the minimum, normal, and the maximum. Okay, minimum, normal, and the maximum. So again, depends on the scenario. We use the maximum since N is like say divided by, right? It's the denominator. So bigger N will give us kind of conservative estimate for the Q and the velocity and everything. So, and most of the time that we use like the middle one, normal. That means I'm not biased to minimum or maximum. I'm using the normal one. So here are the type of the channel characteristics, like arc, straight, and uniform. Then clean recently completed, then it would be 0.016, 0.018, 0.02. And clean water after weathering, then it would be this, gravel, uniform, then it would be this and this. So arc, winding, and sluggish, then looks like a little bit more here. The values are a little bit higher because of the slower light. That then the drag line, excavated or drag, no vegetation, looks like this, light curve, on banks. Then there's channels not maintained, weeds and brush uncut. Then it looks like a little bit like some more, right? Like dense brush high stage, 0.08, 0.1, and 0.14. So it looks like this has that. So in this case, whether to use this, if I can figure it out like which area it might fall under, then the better to use this. So again, these are not theoretically really based things, but the end value comes from different studies and other things like that. So they did a lot of study and come up with the values of 10 for different types of channels and conditions. Selection of design parameters, in this case, sewer pipe materials. The principal materials that are used for the sewer system are asbestos cement, ductile iron, reinforced cement concrete, RCC, polyvinyl chloride, and then high density polyethylene, HDPE. These are the ones used. So I have seen PVC, HDPE, yeah, we use different things in landfill construction because HDPE is very strong and they are very good for using it even deep underground. Minimum sizes. The minimum size are used usually specified in the local building codes or building code or stormwater management or other things like that. So the smaller size used should be the larger than the building sewer connections so that the objects passes through the building sewer do not clog the sanitary sewer. The building sewer connections basically 4 to 6 inch, meaning 100 to 150 millimeter. The recommended minimum for sanitary sewers is 8 inch, 200 millimeters. Sometimes 6 inch, 150 millimeter is used. Yeah, building sewer looks like 4 to 6, and the sanitary sewer looks like 8. 6 can be used, but 8 is recommended. Maximum minimum flow velocities. So here are the why we need the minimum velocity. Minimum velocity we need because of the self cleansing, for the purpose of self cleaning. Meaning, if I don't have enough velocity of flow, a lot of stuff will be settling over here with time, then it will block it, right? It will block the way and other things like that. So that's the reason. Now, 6 to 8 inch diameter pipe looks like the minimum velocity is 3.0 feet per second, 0.9 meter per second. Self-cleansing means kind of minimum, we can say that. 12 to 24 inch is 2.5 feet per second, and greater than 24 inch, 2 feet per second. So we can say, if we would like to put a range, then we say start from 0.6 meter per second or 2 feet per second to, I think it goes up to 10 feet per second, the maximum, or 3 meters per second. And I have it here somewhere. Therefore, if the Q is the discharge, V is the velocity of the flow, and area is the cross-sectional area of the sewer, A is the cross-sectional area of the sewer, then Q equal to area times velocity. This is the continuity equation. So from there, if my Q is known, the V is known, I can assume a V that I can provide there, then I should be able to know the area. If I know the area, then I should be able to calculate the diameter, depending on these, whether it is circular, triangular, or other types. Okay, in general, the recommended minimum flow velocity is 2 feet per second to avoid the deposition, and the recommended maximum flow velocity is 10 feet per second, 3 meters per second to avoid the damaging the sewers. So maximum one we need because if you don't want to do more than that, that will destroy my sewer line and other things like that. Whereas the minimum is so it can keep it clear. It doesn't block the way. Like so any questions? So is it your question is why we need the max velocity? Max velocity is we don't want to go more than that. If we go more than that, there is a pressure creates to the pipe, and the hoop stress and other things. Then pipe will burst out. It has the main problem with the maximum velocity. So 10 feet per second or 3 meters per second is okay. Most of the pipe system that we use that can extend up to that time. So the impulse, right? Impulse, momentum, and other things. So something water is flowing through a pipe, so it might have some effect depending on the velocity in there. There will be an outburst of pressure, hoop stress, mainly hoop stress. Okay. Okay, so selection of appropriate appurtenances, how we can select that based on the sizes of the sewer system. All four appurtenances may be necessary to successfully complete the sewer design and construction. The four appurtenances are manholes, drop inlets to manholes, building connections, and the junction chambers. So these are the one. Okay? So like say, however, junction chambers are seldom necessary. I didn't see a lot. I have seen some areas that have it because of there weren't too many connections in there. Then this is the only how they used. Other than power is heavily required. Evaluation of alternative alignments. Sometimes alternative alignments can be easier to construct or are more economical. As a result, alternative alignment may need to be evaluated. So it's not only the case here. Most of the project, if you are working as a project manager and other things like that, so you guys have seen that. Just a minute. So in this case, we can say that, like say, any project that we work, yeah, so we need to do some kind of alternative analysis. Why? Because we need to see which one is the best option in terms of the cost, in terms of the workability, in terms of the other benefits and things like that. Okay? So that's why alternative analysis is a kind of important for us. Okay? But in these cases, this part is mainly saying that alternative analysis need to be done because if we go to the road system, whether the road is too long, can we go straight forward with something like that? Or we can just do a bending other than going 90 degrees. Because going 90 degrees will have a loss, head loss, right? Due to the bending, 90 degree bending and other things like that. So we'll be losing some energy. So these are different considerations we have to consider and work on that. And any project, so I work for the state, and we had something like that. Our state requiring that you have to have at least 3 alternative analysis before you say that, oh, this is the best option, then I'm taking. So you have to have at least 3 alternative options. And you have to explain with the cost and other things why the alternative that you are selecting is the best one. Okay? So that's why alternative analysis is kind of required by the code, some cases by the management plan and other things like that, by the state, county, or the city, depending on what you okay? So, the curved sewers may be used where they are found to be necessary, economic, and feasible. Okay? So flow velocity may not be the same in all sections of the sewer due to the bending, which needs to be verified, especially for high velocity that may cause damage to the bending sewers. Because of if it is bending, we know that for the impact, right? Impact, impulse, momentum. So momentum is the mass times the velocity. So, and momentums ultimately become force, right? So momentum, if I have a high velocity, mass is flowing, then definitely would be high flow rate, high forces. The high forces, it might break the pipes and other things like that. So that's why velocity ultimately create the impulse, the force, impulse force, and it manage the pipe system and other things like that. Okay, so design of sanitary sewers. Water mains carry water under pressure, while flow in sewers is under gravity. Okay, water mains carry water under pressure, while the flow in sewers is under gravity. It's not always the case. The the idea of the under gravity is always the desirable, but it doesn't mean it's always possible. Okay, because if I'm in a house system like a very low areas, whereas my sewer line is the road is very high, then definitely we have to use the pump. There is no something the gravity will work, right? So, but the most of the cases, more likely, the gravity is the best option. If the switch is to be conveyed under pressure, elaborate pumping equipment is necessary, yeah, for sure. And sewers are designed as open channel using many situations. Although it is closed pipe, but still it can be designed as an open channel because of this necessity and other things like that. And pipe may not be like flowing full all the time. Some cases it may full just half, maybe three-quarter, or half, and other things like that. The design of sewer consists of determining the diameter of sewer to carry the estimated quantity of sewage at a velocity that is equal to the self-cleansing velocity or at minimum. Minimum is the self-cleansing velocity, or it could be a mass. Self-cleansing velocity is velocity that is equal to prevent silting and deposition in the sewer line. So we already defined that. How we follow that. Okay, here is the example problem. We would like to solve an example problem using the Manning's equation that we discussed before, Manning's and continuity equation. Q equal to area times velocity is our continuity equation, and the Q equal to area times velocity, that means K over N, A R to the RH to the power 2/3, S to the power half is the Manning's equation. So, and this one is definitely in a PS system. So I will give you maybe a minute or so, so guys, you can read the question again, like before. So I will read it one time, then I'll leave it there for a minute or so. You guys can take a look. And using the Manning's equation, calculate the velocity of flow V and discharge Q in a sewer of 1.5 feet diameter, laid at a gradient of 1 in 400. Assume sewer run half flow and N equal to 0.02. N value is already given, and it's saying that it's flowing half flow. Okay, and the gradient is 1 over 400, means one drop after 400, 1 feet drop after 400 length. Right, that's what we mean. Diameter of the pipe is 1.5. I'm looking for what would be the velocity of the flow and the Q of the flow. That's what I'm looking for. Yeah, I'll leave it in the screen for a minute so you guys can read it. And maybe solution is there, but I'm going to explain the solutions. But I'll let you read it. Okay, I think we can continue, right? I don't see any questions or anything like that. So, okay, So this is the equation I'll be using to find the velocity. Okay. So v equal to 1.486 by n, r to the power rh to the power 2/3 s to the power half. Okay. Here is the question: what is the typical swell damage caused by high flow? Okay. Do you need to use a tiebacks for class or plots for curve sections? So for the curve section, most of the time we use the velocity sometime less than 10 feet per second, 3 meters per second. But again, we have to calculate depending on how the bending is. If it is the smooth bend, it's not that a big deal. If it is 90 degree, then yes, it is. And the first question I didn't really understand, what is the typical swell damage caused by the high flow? I don't have any experience on that. You mean to say what type, right? That's what you mean to say, either HDPE or PVC or other things. As I said, I didn't see any failure at any one of those because the velocity usually is not that high. It doesn't go more than 10 feet per second. And most of the materials that we use as a swell pipe, they can easily withstand 10 feet per second. So, getting it out of that. Okay, so we'll be looking vehicle velocity. RH is the hydraulic radius. Now we have to calculate the hydraulic radius. Slope is 1 over 400. Okay, so 1 over 400 is 0.0025. N is the roughness coefficient, is 0.012, is given also, right? So RH is the area, weighted area divided by the flow area divided by perimeter. So the flow area would be, since it is half flow, pi d squared by 4 is the area. I put the half over here, right? So pi d squared by 4 is the area because it's circular, and half would be half flow. And then the perimeter would be, since it is half flow, half of the pi d by 2. Pi d is the total circumference, right? The perimeter. And since it is half flow, it will be pi d by 2. So ultimately, if I do the calculation here, this whole thing becomes d by 4. So d by 4, the hydraulic radius of a circular pipe, either flowing half full flow or half full or full flow, then it is d by 4. Okay, so that means 1.5 by 4 is 0.375. Okay, 0.375. I know the hydraulic radius. I know the S value, so I can put into this equation. If I put this one into this equation, 1.486 divided by n, then it would be RH to the power 2/3, S to the power half. Then I come up with 3.23 feet per second. So this is the velocity. This velocity is definitely more than 2 feet per second and definitely less than 10 feet per second. So it is in between the minimum or self-hinging velocity and the maximum velocity. So once I know the velocity, then the Q should be very easy. Q would be equal to area times velocity. So area we calculated here, okay, half pi d squared by 4, so meaning 0.8836. And the velocity we calculated this, so if I multiply this, ultimately 2.85 cubic feet per second. CFS would be my flow rate. So I know my velocity and my flow rate, so looks like the design should be okay. So this kind of problem we can use to see whether if there is already design there, then how much it can carry and what is the velocity. So again, n value, you have to select the n value very carefully depending on the situation and other things. You may have to do a little bit of inspection and select the like n values from the managed table, or if you do the d value, if you can find the d90, then use the other two methods also to verify the n values. Any questions on this problem? Okay, we can move forward. Right. Here is the next example. Example 3. Design a sanitary sewer to serve a population of 5,000 people. If the average consumption is 400 liters per capita per day, how many extra person can be served if the slope is doubled? Using n value of 0.013 in the Manning's formula and the return flow as 70%. Check the minimum self-cleaning velocity, neglect the infiltration and inflow. So here are a few things that we have to understand. There is a question in the source, is the n value for HDP 5? HDP 5 is kind of very smooth. So, and whenever we use this, I think there is a roughness coefficient there, and we can use the value of, whenever we use the head loss, we use the roughness coefficient, okay? Like, so that's the Weisbach equation. So in this case, we use a little bit different way, but for the HDPE pipe, the roughness is very minimal. It's not that high, very smooth inside. So n value, there is n value, but it's not in the list. But as I said, I don't have in top of my head this n value. But there is an n value that we can use. It should be very, very, not that very high value or anything. I mean, small value, or, sorry, very high value or anything, very small values. So some cases you can even use one. So you don't need to use that much. Okay, I'll let you read the question for a minute or so. So we'll be designing one now. The one before example 2, we saw that this was the design is already there. We verified that how long that is, how much Q it can carry, as well as what should be the velocity of the flow. So now here is the requirement is given. We know the population, we know their requirement per person per person consumption, the n value is given, and the return. 70% return means if I have used 100 liter of water, 70% will be sanitary sewer, and the 30% will be lost. Meaning in this case, 30% either evaporated or it has been used in the lawn watering and other things like that. Okay. Okay. So the solution, the population and the thing, everything is given here. This slope here, I assumed that. So because slope was not given, right? Slope was not given, okay? So, but we are looking for, if we would like to double the slope, then how more extra people we can serve. Okay. So this will give us an idea, like say how important the slope is. But again, another thing is if we put too much high slope in high gradient in there, that means we have to go deeper. So going deeper is more expensive, right? Digging, putting those together, and maintenance could be another issue too. If we need to go down that much, we have to dig a lot and go there and do the maintenance. So here I assume, like say 0.005 is the slope, right? Find the velocity, v equal to what? Also check the minimum velocity. And once the slope is doubled, then find the extra population to be served. That's my question. Okay? So part one. Part one means I'm doing this. Part one. So the wastewater flow. P is the population. QW is the one. What percent is the return? And Q is what is the consumption rate per person per day. Okay? So it'd be 5,000 times 0.7 times 400. Okay, this would be liter per day. Then I'm converting into 1 meter cube equal to 1,000 liter, and 1 day equal to 86,000. Excuse me. 1 day equal to 86,400 seconds. If I do that, then the calculation becomes 0.0162 meter cube per second. One thing that I would like to mention here that so the problem before that I did was the FPS system. This one is SI system. Okay, so you have to remember that. So I'm trying to show you both the systems, so we know that how to take out both SI and FPS system. Okay, so then let's take the peaking factor is 3.5. Again, remember that the population is up to 20,000, right? Was 3.5. The peaking factor that I showed you before, the slide 32. So the peak hourly wastewater flow would be waste flow would be 3.5 times 0.0162, ultimately 0.0567, middle 3%. So I know the Q value, right? I know the Q value in this case. Now finding the diameter of the sewer line using the Manning's equation. So Manning's equation, Q equal to AV, Q equal to this, right? So Q equal to this, area times this, 1 over this. You remember that 1 by n, r to the power 2/3, s to the power half. This was the velocity, right? Area is this, and this is the velocity, okay? So by using what? By using the Manning's equation. And why it is 1 over n? Because of the SI system international, SI unit, that's why. So if I take this up to that point, then calculate the value of D. D becomes 1.548 NQ s to the power half whole to the power 0.375. So what I use R equal to D by 4 because I know that the hydraulic radius R would be equal to D by 4 for a circular pipe system. Okay. So in this case, I know my N value, I know my Q, I know my S, right? So all of those. So if I put it together, like say here is the 1, this is the N value, this is the Q, this is the S. So if I put it together, I get 0.663 meter or 2.17 feet. So better to use 2.25 meter or 0.686 meter, okay, feet or meter, by mentioning better. So from this A1 looks like I'm designing the pipe, okay, I get the design system like this. Now I may have to find the value of the velocity just to verify that. Okay, I'll let it here for a minute or so. I mean, for some time to take a look and if there are any questions in the calculation. If you have any questions in the calculation, we can discuss. Okay, so therefore, the diameter of the sewer line D equal to this like so. Okay, this is the without the peaking factor. So these are the one with peaking factor. So what I'm doing here now, this is without the peaking factor. So that means 6.58 inch. Where sorry, yeah, looks like slope, right? Yeah, slope is fine. This is without the peaking factor. Looks like 0.16. So this was 2.25 feet. Now I get only 0.5 feet, right? 0.5 feet. Or other way we can say it is 0.68 meter. Now it is only 1.16 meter. It's far less, right? So use 12 inch. In this case, 12 inch is fine. So 12 inch. Checking the minimum self-cleansing velocity. So we calculate again using the Manning's equation, 1 over n, I could go 2/3 s to the power half. If I use that 1 over n, then this is the like say d by 4. So d whatever the d is, here is the d. So d by 4 to the power 2/3 is this 0.97. So in this case, the 0.6 was the minimum, right? 0.6 meter, and I get 0.97. That's less than 3 meter and more than 0.6 meter. So it is in between my maximum and minimum. So this is just a part 1. Okay, part 2. Now I'm doubling the slope. Doubling the slope means S would be equal to 2S. It's 0.005 multiplied by 2, it becomes 0.01. So then Q would be equal to, again, the way I did it, Q equal to area pi squared by 4, then the velocity 1 over n at 2/3 s to the power half. So in this case, like say, if I do the calculation, taking out all of those, then it becomes 0.21 over n d to the power 8 by 3 s to the power half. How I got a d in there? Because I put r equal to d by 4. So I could have said it somewhere here, but this I put R equal to D by 2. That means that in this case, N value is known, then D value is known, right? Because we are not changing the D value, 0.3048, and the S is this. So ultimately, I get 0.0999 meter cube per second. Then we are converting into liter per day. Okay. So again, this was the main answer, but we convert into liter per day. Now Q is equal to P times QW. So P, number of population, would be Q over QW. So where QW is the return flow is basically times the Q, is 0.7 times 400 and 280. Okay, that means 280 liter per capita per day will go to the sewer. So my population would be liter per day, whatever the liter per day, that is that much, throughout wastewater flow. And this is per person, right? This is per person. So if I do this total by per person requirement, then I get 30,838 person. Initially, we start 5,000. Now, due to the doubling the slope, I got 30,800. So if I subtract the 5,000 out of it, then almost 26,000, close to 26,000 people can be served. In terms of the percentage, it would be what? More huge percentage, right? So, yeah, that was the main idea here, to show like how the slope is very important. Slope can help you a lot. Different cases, if you can arrange the slope, meaning you have an option to have it go to the higher slope. Then the same design, only slope can take care of like some more. Out of 5,000 now, an additional 25. Any questions on that? Okay, we can move forward. Here is the example 4. This would be designed showing a use of different like graphs and other things from the exam handbook and other things like that. So a 3.0 meter circular sewer line is laid on a slope of 0.0009 meter per meter. If n is equal to 0.012 at all depth of flows, determine A, Q and V. Q is the flow rate and the velocity of the flow V when the sewer is flowing full, and the B and depth of flow D when Q equal to just 1 meter cube per second. So this will give us a little bit of critical thinking how to solve this. And using some of the equations, that should not be easy because of, like, say, if I know depth of flow in a 3 meter circular pipe, so it should be very hard to find the area. It's not easy. It's not easy because we have to use a lot of formulas and other things. So other than using a lot of formulas to find the area of the flow area and other things, we have some other way to solve it. Okay, that's what I'm going to show. So given that I used Excel in this case, diameter is 3 meter, slope is 0.009 meter per meter, n equal to 0.012. So I'm calculating the area of the flow. So area of the flow would be pi d squared by 4. So this is pi, d would be 3 squared by 4 equals 7.069 meters squared. If it is flowing full, that's my area. So that's why I said area F, area full flow area. For circular pipe, full and half both are each equal to d by 4. So d by 4, d is 3 meter by 4 is 0.75 meter. Using the Manning's equation, v equal to 1 over n. Why it is 1, not 1.86 or 486? Because of this is SI system. So, and if I put this value together, 1 over 0.012, then our H is 0.075 to the power 1/3. then 0.0009 to the power half, I get 2.06 meter per second. So this can be considered as when it's flowing full, right? The velocity when it's flowing full. So Q equal to area times velocity. So I get a Q equal to 14.587 meter cube per second. So this Q is definitely when it is flowing full, right? When it is flowing full. So I got the velocity when it is flowing full is 2.06 meter per second, and the Q is 14.586. That means A is done, right? A was easy to do it because it's flowing full. So I should be able to know how much Q this pipe can carry and what should be the velocity. If I compare the velocity, 2 meters per second, definitely it is more than 0.6 and less than 3 meters per second, right? It's in between. Now, part B has a little bit of different way of solving it. So, for part B, Q is given 1 meter cube per second. Let's assume the depth of the flow for given Q is equal to dv. Now, Q over Q full. Q, that means this. Okay? And Q full already we know that, 14.587 from the previous slide. Right? So, from here we know that. So that's what I'm putting in here. I get 0.0686, 0.0686. Now from the following figure, Q over QF equal to this. If I have this value, then D over D equal to 0.2. So I said red and green arrows. So let's go back to here. I have to remember this, 0.0686. So if I come here, so what it says, what lines are? The red and green. So red and green means this and this. So what I had a Q over QF. So let's see which one is my Q. Okay? So these two curves are my Q, like this one and this one. Okay. Now why I'm using the dotted line? Because the dotted line looks like N and F are constant. So N constant, F is also constant. And N is the friction, roughness coefficient, and F is a friction coefficient. So that's why I'm using the dotted curve. Okay. So if I know my 0.068, something like that, because 0.1 is here, 0.0686, then I go back over here, hit the curve. Then if I hit the curve, go back here, I will know d of small d over capital D. Small d is the depth of the flow, and capital D is the diameter of the pipe. So I get 0.2 from here. So this is the value I got. So that's the one I'm just putting here. Okay. So if I know d over small d over capital D is equal to 0.2, then like say small d would be equal to 0.2 times capital D, right? So capital D will already know is a 3 meter diameter, so I got 0.6. So in this case, when the Q is flowing 1 meter cube per second, so depth of the flow would be equal to 0.6 meters. Okay, it's 0.6 meters. So it's not half of the radius. Radius is 1.5. So it's not half flow, it's less than half flow, right? For 1 meter cube per second. So from the following figure, for d by small d by capital D equal to 2, I need to find the area over area fold, and also velocity over velocity fold. So so I'm using the blue and green arrows. So blue and green for that, and black and green for this. So if I go back blue and green, so blue and green is this. So green is here, and I'm using the area curve. This is the area curve. So if I come here, it looks like 0.13 or 0.15, whatever I use here. Looks like 0.13. I use 0.13. Then V over VF is 0.56, black and green line, green arrows. So the black here is the black. So I came from here to this, and this is the one is the velocity. And why I'm using the dotted line is because the same concept, N and F are constant. So if I go back here, it looks like 0.56 or 0.55, so very close to like that. So that's the value I have, 0.56 here. Now area of the flow, I know this is the full flow area, AAF. You remember that 7.069 was right here, right? So then if I multiply with 0.13, I get 0.919. So that means the area of the flow for 1 meter cube per second would be 0.919 meters square, and the depth of the flow would be 0.6. And the velocity of the flow at that time, 0.56 times velocity when it's flowing full is 2.06, ultimately would be 1.16. So in this case, the velocity V over Q, if I calculate that way, I can do this way, or I can calculate using the Q and the area. So I get 1.09. So this seems to be 1.16 and 1.09. Both are very close. They're not that far away, but we should check for both. Checking for both would be a very good option, best option. Okay, this problem is a little bit tricky in different ways how to use the graph. And this graph, I took it from the exam handbook. The figure 10.1, the exam handbook, page 160. So this can help us to solve some of the problems. This problem can be solved by using a lot of equations, like a lot of derivations, but it's not very easy. Main issue is if you have a circular pipe, and only partial flow is happening that is below the center point, then it's not easy to calculate the depth and the depth. Depth is even there to calculate the perimeter and the hydraulic radius as well as the flow area. Even if it is above the center line, then it's also the same. But if it's flowing through the center line half flow, then everything is known because we know all the formulas. So any questions? I'll leave it here for a minute or so. I think we have enough time to finish it. So we have 30 more minutes to go. Any questions? Okay. So contract drawings and specs. Example construction drawings reference 1. So this shows like say the profile view. Profile view in this case, this is manhole number 1, then manhole 2, manhole 3, manhole 4. So I have here manhole 4. So it looks like going this way. This part is straight, this part is straight, this part is straight, right? 3 straight lines. 3 straight lines. And how many slope I have here? From here to here is the same slope, 0.014. And from here to here, what slope is that? Looks like maybe a little bit of slope, but it doesn't say exactly the slope, right? We should be able to find it. Or yeah, a little bit of slope here, not a whole lot. And from here to here, manhole 2 to 1 is also like 0.002. No, it's a little bit smaller than this, right? This is 0.014 and this is 0.004. And this will help us, like, so these are the elevation, meaning inverted elevation is 50.87. Station is coming from here to here, 150 to 40. And 50 means if I take here, this point, it would be like 50.87 elevation compared to the baseline, whatever the baseline is. Here it is 50.66. It's not that much different, but a little bit low. Then here it is 48.94, and here it is 52. So that means it's going down, little down, little down. And here are the locations of the manhole. These are the ground surface. This will tell us the depth, right? If we know the scale, then we should be able to know what is the depth that we have to cut here and fill later on and other things like that. And this is the profile view, and this is the the plan view. Okay? So this will tell you the name, the location of the manholes, and the diameter of the pipe. Looks like this is 200 millimeter. And this one, this is another gas line, and this part, it doesn't say anything, looks like, but I'm assuming it to be 200. And this one, 0.2 kilometer, and this is water line, looks like there is a water line here. This is a manhole 4, and this is the distance, kilometers, showing 70 kilometers. And here is the manhole location, manhole 2, the same station here. And it's matching with this, right? Whatever is shown here is matching with here, and so on. So this kind of drawing are used to, like, so when we do the construction, and other things like that. You need to exactly sure. You need a surveyor and other things, stakes and other things like that. So any questions on that? Okay. Specifications for each component of the project are important for bidding and construction purpose. So this will be showing the drawing. Okay. It doesn't show like say what kind of quality of the pipe, this one, right? Even in here, even it doesn't mention that it is PVC or other things like that, right? So meaning the specs should say what kind of pipe we're using. Specs is very important for bidding purpose because if you put the specs together, then the whoever the companies are bidding your project, they will know what kind of materials you want. Then they'll give you the price. Like so they'll be using that kind of materials. So that's why the specs are very important. Sample specifications for HDPE pipes and manholes can be found in the literature. But again, a lot of those can be found, but you can probably prepare it as a consultant or project engineer. But I have some examples that I think I worked on those before. I may be able to show you some of the examples that I have. Construction of sewers. The construction and layout of sewers consists of the following operations: setting out the alignment of the sewer lane, setting out, set out, excavation of the trenches. Here the example showing the excavating. So they excavated and put some bedding materials over here for the strength of the bottom of the pipe. The branching and dewatering of sewer line. Okay. Then laying pipe and joining the pipes. Okay. Once you lay them up, then you have to join them. That's here that they already have joined. It could be dead end or something like that. So, and then the testing, backfilling. So we have to do the testing whether the pipe is probably here okay or not, especially the settlement part of it, maybe. Huge differential settlement might break the pipe and other things, but most of the time, if we do the bedding materials and compress it properly, it's okay, backfilling, once we are done, backfill it and put the grass on top of it, sealing, mulching, whatever you have to do. So to reduce the scouring, right? To reduce the sedimentation and scouring of those things. So we have to have it. Okay, here are more examples with this thing. Here are the guys, I think looks like they are backfilling and making something like that. Or maybe they are doing the recognizing side. Other two probably saw those before. The maintenance of soil. Keep sewers clean of obstructions and in proper working order. Clean with special tools where flushing is inadequate to remove an obstruction. Special tools, or if it is too big pipe, but in case we have seen the 5 feet pipe, then you can send a people. So, and they can clean it up over there, they can dig it out, or with the smaller 8 to 10 inch pipe, flushing, and other tools, pushing tool, and other things like that. Provide proper ventilation for removing explosive gases, methane, carbon dioxide as they form due to the decomposition of waste. So methane and carbon dioxide are formed due to anaerobic decomposition of organic materials. And most of the time, whenever we have the wastewater flowing through the pipe systems, sewer pipe, they have some organics, means barely, right? Yes, like barely. So in this case, they will decompose due to the absence of oxygen, as then it will create carbon dioxide and methane. Methane is very flammable. Carbon dioxide is bad for us, right? Because we expel carbon dioxide, we don't want to inhale it, so it will not give us good feelings, or it will not clean our blood. Our blood needs oxygen, right? Not the carbon dioxide to clean hemoglobin. Okay. So here are some of the specs that I have. This one looks like high density polyethylene and appurtenances. So the part one is mainly general, then the work included, what kind of work it will explain, then the related work, and under the related work, there are some of the related sections. So like say 0200 artwork, sorry, artwork, not artwork. Artwork means whenever you're doing the artwork, you are digging how you are managing the art and other things like that. It will explain those part of it. And whenever you are doing this HDPE pipe, you have to do that because HDPE pipe is you are digging the soil, then putting to the soil, you are refilling it, right? So in order to do that, you may have to follow the artwork facts too. Section 02400, polyethylene, uh, polyethylene geomembrane. So in this case, geomembrane may be used to, like, say, what is the geomembrane? Geomembrane is the one kind of plastic the sheet, mainly, like plastic sheet. So sometimes you may have to use it. And the third one is the geotextile. Geotextile is wave or non-wave, or whatever you can call it, non-weaving and weaving. Um, so geotextile is used some kind of, like, say, um, to the screening of the materials. So certain cases, if I don't use the geotextile, maybe some of the materials will be washing out. So better to use some kind of geotextile. Then geotextile will let the water get out, but it will keep the other material. The standards, work shall comply with codes and standards of the Plastic Pipe Institute, PPI. They're mentioning. The references here are the references for the testing. Okay. So in this case, ASTM D638, tensile properties of plastics. Then the 790, flexural properties. 1238 is flow rates, thermoplastics by expansion. Then 1248 is polyethylene, plastic molding and extrusion materials. Means in this case, if they want to do welding and other things like that. And here are more, D1505, density of plastics by density gradient techniques. These are different testing methodologies. ASTM, American standard testing and materials, right? Any standard for testing materials. So ASTM. So these are the ones you have to explain. So the bidders, they know that you are looking for those. If you ask them, okay, you have to have those kind of facts. You have to use those kind of methodology to do the testing for the especially quality control and quality assurance, QA and QC. Submittals. The contractor shall submit evidence of the qualifications required by the CPA plan and any other such pre-qualification data. Okay, the references and project expertise, experience information as requested for the project. Contractor shall provide manufacturer's technical data sheets for the following: SDP pipe, SDP appurtenances, SDP manhole. So it looks like SDP manhole can be used also, right? So what about the manufacturer provides? They have to provide the data to the company. So whenever you are bidding, so they know that you are using the same one, whether it's used for requirement or not. Provide all test results of the SDP piping system, manhole prior to the submittal of completion of the project. Okay, these are kind of conditional contract. In this case, leveling, delivery, storage, and handling. Leveling pipe, including manhole delivered to the site, shall be new, clean, leveled by the manufacturer with the following: manufacturer's name, nominal pipe size, plastic type, standard dimension ratio, SDR, and the extrusion date, period of manufacture lot, and the batch numbers. So these are the one has to be. Delivery, the pipe should be delivered to the site. Again, depends on how the contractor is doing it. The pipes that should be rejected due to the irreparable damage. So there is a condition over there. So that means if some damage just happens, then they should have an option to return. They don't need to accept it. The storage, so there are some requirements for the storage where you can store it so it doesn't get damaged with the time, before the time it's like construction or anything like that. The manufacturer representative shall have the right to verify that the pipe and the premises are stored in accordance with the manufacturer. It could be checking from both sides. It's from the company that you're working for, it could be from the manufacturer too. So when we are buying it from the manufacturer, we give them some kind of contract or the idea of how we will be handling those. Okay, the handling, contractors shall be responsible for all on-site handling of the pipe and appurtenances. The pipe and appurtenances are to be handled so as to prevent damage. So if they don't handle it, they don't make it secure, then somebody else may come and break those, and in this case, it will last. Manufacturing representatives shall have the right to verify the following: so handling equipment and control personnel knowledgeable whether or not. So pipe and appurtenances are damaged or otherwise determined to be unsuitable by the owner or the engineer following initial storage accompanied by these things. shall be replaced by the contractor at no additional cost to the owner. So it's also part of the contract. So there is a lot of things can be used as a part of the contract, payment contract, and other things like that. Okay. So here are more requirements. Contractors shall have at least 5 years of experience. So any new, they don't want to use any new contractor, looks like. The contractor is required to demonstrate compliance to the above requirement to the satisfaction of the owner or engineer. Part 2 is a solid wall pipe, acceptable manufacturer. They are even mentioning what kind of manufacturer they'll accept it from. Flexco, Phillips, Visco, Polypipe, Approach. These are the name of the company. Manual materials shall be extra high molecular weight, SDP type this. That means what kind of resin they can use to build those or make those. And pipe shall be STMB type 111 class C category 5 E34 of SDR. So these are kind of like code names in here. SDR means standard dimension ratio. SDR, I think, is diameter by thickness, right? Outer diameter over the thickness of the materials. So, ASTM D3350 minimum cell classification value 345434C. These are the ones they will know it. I don't have any idea on that thing. All pipe and fittings shall be provided by a single manufacturer. Okay. So then SDP pipe shall have the following physical properties. Yes. So these are the one: density, melt flow index. These are the physical properties. Some of them, structural modulus is not a physical property. It's definitely chemical properties, strength properties, hydrostatic design stress, and other things. Here are the numbers. Should be around this or more. Fittings 3350, but the fusion model or factory fabricated. Fittings shall be pressure related. So they have to do some kind of testing. SDP manhole, here is some requirement for the manhole and other things like that. So thermal welding material. So these are all for, the requirement for the SDPE. In execution, means the contractor shall have an individual experience in the installation of the SDP pipe. They have to have some kind of experience. Contractor shall provide all requirement certifications and technical data sheets for all of the piping companies. Meaning they have to get a permission, or not a permission, certification from the manufacturer saying that, they are qualified to do the installation because they went through the training process. There are people, managers, and everybody went through this, so they will be able to install it for you. This kind of qualification, pre-qualification. Quality control. The quality control is mainly when something is being constructed, even pipe is being made to the company that can do the quality control. Quality assurance, that means once we make it, then we take some sample and test it and make sure that it maintains the quality during the construction, or it has things like that. Here are more on the installation part of it. So they said how to install it, if you need to do any welding or any connection, what kind of connection should be there. Okay. Inspection of the piping hole is back, and when you certify that the inspection has been done. Solid wall piping joint. Yeah, here we go. The joint, whether the joint is just plug in or they have to do welding or anything like that. So joint has to be like male, female, so they just plug in itself to each other. So in this case, definitely welding, if the welding is not required, or for the water tightening is not required, then just pushing it in is fine. So these are very kind of pipe placement, the option like that, placement of SDP manholes, because this is for both, right? Manhole and SDP pipe system. So here are some of the way to do that, things like that. And embedment and backfill. So they have a requirement for the backfill in 2200, right? Section 2200, we mentioned the artwork. So this will be something like that. Then the post-main testing. Post-main testing, once we put it in there, we have to test it whether it can take the pressure or not, something like that. Uh, in order to do the testing, you have to prepare it and things like that. Test procedure, they will mention what kind of test you have to do, what kind of procedure. Acceptance, what kind of test result within the values, accuracy and precision, you will accept the test result. Test pressure, how much pressure you need to do. In this case, HDPR looks like 10 psi ER for a period of 20 minutes. If you put it in there and they withstand, that means you are fine. So that means your test is done. So here more part of the test, date of test and description, what kind of test we did it, whether they certify it. HDP manhole, hydrostatic testing. Hydrostatic, you know that if the water is not flowing, it's still sitting, then still how much be the pressure in there, whether it can withstand it. Okay, here's the manhole, 2520 section number. It's the same. Initially, they discussed like what is the manhole means. You know the manhole already, right? So you don't need to worry about it. Design requirements, submittals. So this one. Products, again, quality assurance, quality control, precast concrete manholes, if you would like to do that concrete or HDPE. They might have different options, either concrete or HDPE, both can be acceptable or something. Okay, so looks like the summary. In this webinar, we have defined several terms related to wastewater collection system, discussed the different types of collection system, types of sewers, shapes of sewers, and the collection system effectiveness. We have also analyzed the basic considerations of sewer design and worked out a few simple design problems in the widely used many situation and graphs from the API exam handbook. We have been familiarized with the construction specs of HD types and appurtenances, meaning I explained a little bit here. So I'll come back to this question. We have a question, looks like why do you go to answer the original questions? I have something afterwards. So here are the references that I have used for this, preparing this. A lot of engineering by our TV and his colleagues. Hydrology and hydraulic system by Ram Gupta. And the exam handbook and my personal work experience a little bit, not a whole lot. But personal work plus teaching experience I have used. Okay. So here is the one. So you can email me directly for any questions that you might have, or you can email the PDA source. They will probably contact me, or you can do direct. It doesn't matter. You can write down this email address, or if you would like to get these slides, I think the PDH sources should be able to send you the slides for you. Okay, so looks like it's a good timing. I have 10 minutes for question and answer. You can hang around and ask questions and answer. So So there is a question like, are these concepts, okay, there are big questions here. Okay, let's go one by one. So are these concepts applicable to healthcare facilities? What do you mean by healthcare facilities? Healthcare facilities is the same as industrial or business entity, right? So this concept, whatever we used here as a part of the like say collection system, yeah, we can use HDPE, we can use PVC pipe. It's the same as the construction of the other things. So I think everything is applicable to healthcare sector of healthcare facilities. I don't see any differences in this. Because the same types of the wastewater will be generated. Some of the hazardous part of it, I think even the HDPE, some of the other type PVC, there are a lot of chemical resistance. And I don't think even we generate a lot of chemicals, chemical waste or anything like that in the hospitals or healthcare system. Because these are the most likely when we create some hazardous waste, they have to be managed differently. They cannot be discharging directly to the storm sewer or the domestic sewer line, so or even industrial sewer line. Okay, so So there is a question, further question here. Hospitals such as ambulatory care centers. Yeah, I think everything is fine. As I said, we are carrying the liquid waste. We are not carrying any other hazardous waste or anything like that, right? If we have any liquid hazardous waste, then it depends on whether they want to just put it in there. If they do something like that, they can do with a pre-treatment. They can do pre-treatment, industrial pre-treatment. There is a option that we use. And after the industrial pre-treatment, they are free to submit it to the regular wastewater treatment collection system. So there is another question here. In a combined gravity or pressure system, the size of pump station sump is determined by the discharge weight into the sump and the cycle interval of the pump. What is the desired cycle time for the pumps? So cycle, it could be like, say, I did a little bit of design work in the landfill, sump and other things like that. So landfill, we do the same thing. Landfill, they have a leachate. We collect the leachate through the perforated pipe system and come to the sump. And the sump, we have a pump already connected to the sump, and we just pump it out. So the pump the cycle is I don't know whether you mean to say the design cycle is basically kind of automatic. If it's submersible, then if the water level comes to a certain level, it automatically starts the pump. So you don't need to, like, say, manually start the pump. Okay. So in this case, it is cycle is like, so whenever we have a certain depth of the water in the sump, it's automatically pump out by the pump. So pump design, submersible pump design can be done depending on the horsepower and the Q, how much Q we are delivering to the pump. Hope I answered your questions, right? The control is, I think sensor control, I forgot exactly what kind of control we used in there in the landfill one. Landfill leachate is a kind of, like say, most of the time it is vinyl chloride in there. So vinyl chloride, it's not like say harmful to anything, but I think there is a, I forgot the word, there is a sensor. There is a sensor thing can be used in there. So mean sensor is sensitive to the depth of the water or the floating or something like that. If it goes certain level, then the pump starts automatically. Uh, Floats, yeah, floats are fine. Yeah, somebody says floats. Yeah, I think floats is another good option to use. So floats are fine. And the sump size, if you want to consider the sizing of the sump, so depending on how much leachate or how much, like say, wastewater you are generating, then and how long you want to store with a depth, then your pump will start. So depending on, you can do any size, but reasonable size is better. So the pump can run at least for a few minutes before it stops. So. I'm not familiar with those two setup that he mentioned. Can these some pumps be set up with Modbus or backnet controls? I'm not familiar with those. As I said, we use some kind of control before. It was like sensor, type of sensor thing. But for some number of years, I'm in the university. I'm not involved on those anymore. So can this some pumps be set up with BMS and BAS? I'm not even, you have to explain the terms to me. BMS, I'm not familiar with BMS and BAS. Matthew, please like elaborate the two terms so we can see what they really mean. And even if somebody else know, please post it in here so we can learn from each other. So. Okay, control first to see pump status on a workstation. Oh, okay, SCADA, right? SCADA, you mean to say SCADA. Okay, I'm familiar with the SCADA, meaning like say control system, like say remote kind of control system. You can take a look in the screen and what is happening here and there. Yeah, I know that part, that we use a lot of those in wastewater treatment plant, basically, and water treatment plant also. To see the water level and the pump, which pump is running, which pump is not running, and automatically if there is a malfunctioning, then we can see those one. Yeah, these are the SCADA system can be used in anywhere. It can be customized for any part of it. Do this system require commission? Again, I think it depends on, yeah, it might require, or it may not. As I said, I'm not involved in for the last, what, 12 years on those things. So I don't know. Anybody can help us on that to answer this question? Do these systems require commission? Any other questions? Still, we have a couple more minutes. If we don't have any questions, I don't think this is an issue to probably finish it here. So we can probably finish, and we can end the webinar here if you guys feel like. Feel free to drop now, or if you have more questions, feel free to ask more questions here. Thanks, everybody. I would like to thank you for listening to me. It was good to be here. Thanks to everyone.